SwayamPrabha. Digital India. Educated India.
So, you have got some introduction of the how to make a material tough. There are intrinsic ways of doing it, there are extrinsic ways of doing it. Intrinsic ways are related to metallic materials, extrinsic ways has to do with the ceramics. Ceramics are traditionally brittle, therefore, the microstructural engineering has to be done to increase the toughness. So, and we have been discussing about those means. Those means one of the ways of doing is crack deflection, other way is basically what is known as let me just go back to that. Other way of doing that is called zone shielding, and one of the ways of zone shielding is transformation toughening. So, as I discuss again, I go back to zirconium oxide. Zirconium oxide can have three different polymorphs, cubic, which is stable from 2370 to 2680 degrees Celsius temperature, very high temperature. And this is then there is a phase called T phase, which is known as tetragonal with the C by ratio is 1.02. It is stable intermediate temperature from 1240 to 2300 centi, and at lower temperatures from 1240 to room temperature tetragonal phase is stable. Remember here the bigger atoms are actually bigger, blue circles are basically oxygen, and the green ones are basically from the zirconium. So, like here in cubic, zirconium atoms are sitting at the phase center cubic positions for these. So, there are 8 atoms sitting, and oxygen atoms, zirconium atoms are sitting at the tetrahedral voids. So, similarly in tetragonal, monoclinic is a little bit distorted structure because it has a lower symmetry. Now, as I showed you in the next phase diagram, which I am going to show you, that it is possible to stabilize the cubic phase at lower temperatures by adding the second phase, either magnesium oxide or yttrium oxide. You need to add more in magnesium oxide, less in yttrium oxide, but the effect is same. So, the phase diagram which is for the zirconium oxide, magnesium oxide phase diagram tells you that the cubic phase can be stabilized at lower temperatures. Now, the way of doing the microstructural engineering is just what I discussed. If I take the zirconium oxide, magnesium oxide, 10% magnesium oxide sample, heat it up to about 2000 degrees Celsius temperature, it will be completely cubic phase. Now, once it's intermediately cooled to about 1500 degrees Celsius temperature, part of the cubic phase will be transformed to tetragonal, not all, and that can also be determined using these tie lines, how much will be tetragonal, how much will be cubic. Obviously, tetragonal will be very low because this will be depending on these arms. That can be done effectively by controlling the temperatures and also the time. So, whatever way we heat treat in the intermediate temperature range, this will produce some tetragonal zirconium oxide in the form of some rods. Then once you cool it down to room temperature, these tetragonal oxide crystals, the zirconium oxide crystals will or materials or phase will be transforming to monoclinic, and this transformation requires a volume change, and that volume change can induce stress. So, let us see some of the microstructure. Like here, I am showing you some microstructures which is taken from again the Carnegie Mellon website. As you see, sintering was done here at 1800 degrees Celsius temperature at first, and then at 1400 later on. So, when you hit sinter at 1800 degrees Celsius temperature, this will form a completely cubic zirconium oxide phase. At lower temperature, 1400 degrees Celsius temperature, there will be transformation from cubic to tetragonal, as you have seen in the phase diagram also. After 4 to 5 hours, tetragonal precipitates grow by conventional diffusion process as coherent spheroids along 001 of cubic phase. Crystallographically, they will be growing along 001 planes of the cubic zirconium oxide phase. Now, below a well defined critical size about 200 nanometers, the tetragonal particles will remain tetragonal even down to room temperatures. So, that is not helpful. That is why we have to increase the size of these, because there is a size effect. If you make the size smaller, the transformation may not happen if you cool it down to room temperature. That is why 4 to 5 hours are required for these tetragonal zirconium oxide precipitates to grow within the cubic phase, and optimum microstructures should be containing about 25 to 30% of the tetragonal phase. That is what is people have observed, researchers have observed by doing experiments. How the things happens, this is very interesting, that is what you have to focus. Now suppose I have a crack in a material, or I have a crack in the material, means zirconium oxide which is stabilized by magnesium oxides or yttrium oxide. So therefore, there will be the tip of the crack is very, very small, and there will be huge stress concentration. Why? Because load is same. So if the size is small, area is small, the stress is higher, because the crack tip is a very thin layer. So therefore, that is surface, the area is very small. So therefore, there will be stress concentrations, and these stress concentration regions tips transform the surrounding zirconium oxide particles or inclusions, whatever I say, to monoclinic ones, because these particles which are present, these are the particles just shown here. Okay, you see here, these the blue color particles which are shown here. So these the crack tips, these ones has not transformed anything from tetragonal to monoclinic. They remain as a they have transformed tetragonal to monoclinic structure, and beyond that, I think at the ahead of the crack tip, much large farther away, they remain as a tetragonal. So we will discuss why these stress can actually act as a triggering point for them to transform from tetragonal to monoclinic. So these are the stress orientations, the red arrows, and therefore the zone which has been marked by very fine dotted lines is called the transform zone. Remember, as it transforms to monoclinic, what will happen? There will be volume change, and volume change will lead to compressive stress development around the tip of the crack. So as the compression stress will act like this will lead to closure of the crack, not actually opening of the crack. As the crack actually get closed, so therefore it will not be able to propagate. So or rather, if you want to open the crack, you need to apply more stress or to open the crack further. So by simply having a transformation from tetragonal to monoclinic, we can actually increase the toughness, even increase the toughness possible, 1 order of magnitude increase is possible by in this case. That is what is interesting, and this is what is known as transformation toughening. You can see here the lengths of tetragonal inclusions, these are tetragonal which is in a cubic matrix, they are close to about 200 to 50 nanometers, okay, and it can be even made larger. These are the ones when the crack moves, these precipitates actually get transformed from tetragonal to monoclinic. Second way of doing this is another way. You can also have a micro cracking around the transformed inclusions. Let me just explain to you. See, if I have one crack going like this, then moving of the crack requires tensile stress. Okay. Instead of that, if this crack actually becomes like this, there are a lot of many micro cracks forms, branch micro cracks forms. Each of these crack require a stress to move, because surface area, surface energy, as the crack moves, it creates two surfaces, very simple. So therefore, as one crack moving, the increase of the surface energy is smaller than have many branch cracks, very simple. So that is what is known as micro cracking. If I have micro cracking around the transformed inclusions, micro cracking means very small level of cracking, very small level of cracking. This one I have drawn is even bigger, it can be smaller. The volume stresses resulting from the tetragonal to monoclinic transformation delocalize the stress from the crack tips. Okay. Simple, the same idea. Basically what it is showing in this picture is that this red color region is basically volume of tetragonal zirconium inclusions, and this one is a volume after transformation. So there is a volume increase as you know, and the red arrows show the stress due to volume increase and microstructure due to the volume increase. Okay, like these are the cracks. So because of the stress which will be primarily compressive, the crack which was even branched which will be also closed, correct. First thing is that the crack has become branched. Second thing is that these states also allow the branch cracks to be closing, both are possible. So that is the another way of increasing the toughness. First one is a simple transformation induced volume change, second was transformation induced plus micro cracking, both it can lead to increase of the toughness. Both actually can operate together even inside the material, and it has been observed that these features are seen in the real microstructural features. Third way is I discussed already, is known as because of the crack deflection due to volume stresses. The crack which was moving like this is the crack, you see here the red color one. There are precipitates lying these kind of regions. So because the red color region is basically the tetragonal volume due to tetragonal, and the blue color is the volume increase because of the transformations in each case. So because of volume increase, what will happen? The region here will be tougher because the compressive stress has developed. So crack cannot pass through it. Crack will then propagate through regions where there will be less compressive stress or most tensile stress rather, because it can open and move fast, and in this way it can follow a treacherous path, or it can actually deflect. It can easily deflect through these and then follow a treacherous path, and this can lead to toughening, because the moment crack follows a longer path and the crack is requires movement, requires energy. Why? Because you are creating surfaces, the surface energy needs to be provided to the system. So there are three ways of doing this kind of transformation toughening. The phase transformation is very simple, tetragonal to monoclinic, volume change about 4.7% increase, but the modes in which it operates can vary. It depends on whether you have a simple crack like that one I showed you, okay, moving, and near the crack you have a transform zone, and the transform zone can lead to compressive stress. Or you can have a situation in which you have micro cracking and also closure of the crack tips because of the stress generated during transformations. And third one is the crack deflections. So that means in one transformation I can actually bring in, or with the system can bring in 3 different modes of toughening. And that is why zirconium oxide, partially stabilized zirconium oxides are more widely used in the bulk ceramic applications. And please remember, these transformations similar transformations also happen in metals. In fact, many of the transformation in metal also can lead to volume change. Volume change means positive change of volume, and positive change of volume lead to compressive stress development. And this is used in many of the metallic system, also in steel also it is used. Some of the cases austenite to martensite transformations, austenite to benetic transformation rather, has a volume change, and this can be used for toughening. But there what happens, because it is a metal, there is a lot of intrinsic way of toughening, therefore this is not very prevalent, or it does not contribute extensively for increase of the toughness, so never used. But in this case the phase transformation from a tetragonal to monoclinic can be used to induce toughening in the material. So now in some of the pictures, this is again, you see the twin zirconium oxide particles, inside there are twin plates, okay. Each of these particle is shown, cubic zirconium matrix which completely transformed to monoclinic structure, and this twins basically forms because of the transformation from tetragonal to monoclinic. This can lead to twinning inside the zirconium oxide particles. So that is what is showed, bands within the inclusions are twin lamellae, and twinning can also lead to toughening. We know that twinning can accommodate huge amount of the strain inside the material, and more the strain accommodation, more is the energy required. So this is also something which is, that is what I say, 1 transformation happening 1, transformation happening 2, transformation happening 3. The 3 modes are clearly depicted. Please remember these, because this is important. Those of you who will be who are dealing with zirconium oxides or partially zirconium oxides, sometimes we tend to miss these aspects, that even during transformations from the tetragonal to monoclinic, there will be twin formations, and these twins can increase the toughness, because both the toughness can, because twin can accommodate huge amount of the strain compared to other means of deformations. Okay, and I will not go into details of these aspects, these are all there in this lectures. Just to tell you that transformation, how does it actually operate, and these pictures are taken from this website vertebrae.ae. Okay, you can actually see from this is just clicking it, you can actually see. So this let us look at very simple in next couple of minutes time. Consider the effect of tensile stress in the vicinity of the crack tip. Obviously only when you apply tensile stress the crack tip will move. The stress removes the constraint on the each particle, because these are the tetragonal particles as you see here within the cubic matrix, and this is what is shown here. And once you apply stress, this will remove any constraint for transformations. Constraint means what? As I showed you, the sizes of the zirconium oxide particles are tetragonal particles are more than 200 nanometers. This may not transform to tetragonal if you cool it down, monoclinic if you cool it down to room temperatures. So therefore, what will happen if the stress can actually trigger the transformations, because stress can lead to volume change, and the volume change, because as the monoclinic requires higher volume, so the transformation can happen. So transformed particles are metastable thermodynamically, so remains in the tetragonal monoclinic form even after the crack has gone. Okay. The stress acting to cross the transformation chain performs a work. Yeah, it is performing some work, so therefore energy consumed in the phase transformation. Energy or work done adds to the surface energy required to create the crack length. That is also another important aspect which you should remember. This is the fourth one. So the stress which is acting to cross this transformation from tetragonal to monoclinic, can cause a strain, and if it causes strain, that means it works. Energy is basically stress multiplied by strain. So if the stress causes certain kind of strain in the material, it also energy is required. That energy goes into adds to the surface energy and to create the crack length. So this is also another important aspect. Here you see this is the transform zone which is transformed to monoclinic particles, and even when the cracks has moved, still the monoclinic particles, monoclinic transform regions remains. Okay, so that is the another aspects which you should also keep in mind. And this is exactly showing the same thing. Region in which the transformation occurs become a crack wake. As the crack propagates, region around the crack tip is known as a process zone. Just to let you know that this is the wake which is transformed, and this is what is the frontal zone which is yet to transform. So these are the transform zones which can actually reduce the or increase the toughness of the zirconium, partially stable zirconium. Okay, these are the particles of the zirconium oxide taken from again another paper by Chiang et al. And it can be shown that lenticular separate stabilized zirconium oxide particles exist in this, and they can transform. Well, that is about the transformation happening, and with this I conclude my lectures on this course, and I hope at the beginning of the semester I just in the very first lecture I told that the idea of these courses is to let you know the different kinds of phase transformation which happens in metals and some of these in ceramics. Mostly the important one I discussed. There are other transformation ceramics which I could not get time to discuss because course was structured basically for the metallic ones, and I just wanted to take this one to show you that in ceramics also it is important to understand phase transformations. So in a nutshell, that if you go back, you will probably have an idea that different phase transformations are very important in metallic systems. And it is important that you understand these, because finally what we are doing, we are basically controlling the important parameter of the material, that is called microstructure. So if you want to design a new material by controlling microstructure, you have to understand phase transformations. How the different phase transformation actually occur in a material or in different materials, and what are the different thermodynamics and kinetics of these transformations, because these are the tools which allow you to understand the phase transformations. And I hope you have enjoyed the content of the course. Some of you already have written some emails and other things. So, this course will remain as a repository in the NPTEL, and hopefully later on when as the demand requires, this course will be run, but I do not need to take the lectures again, all the lectures again. Even if it is required, I can change some of the lectures, but obviously all the lectures will never be required to be recorded. Okay, thank you for your patience, and I hope you will keep it interesting till the exams are taken.